Thank you, Mark. That's a very generous introduction. I should say I'm super excited to be here, and I should mention a few things, Mark, that I didn't know. I worked at Johns Hopkins for a few months, many years ago, and about 10 years ago, Sanjeev, Jason, and a bunch of other people in this room organized workshop, speech recognition, and I was here. And I think I was in this room too, pitching proposals with Jeffrey Weiger and everybody else. And luckily, the proposal was proposed, and Sanjeev were talking about it. I bought a GPU card with a bunch of Tiger Direct, the component-based computer. My student and I, assembled. Quickly, things started running, and a few days later, I think the GPU starting to burn out. The pop sound, the smoke, and everything come out. So we officially burned our first GPU in Johns Hopkins. I forgot what's the name of that hall now. Sheffield, okay. But it's a good fun memory of coming back here, and I think this is actually my first in-person talk after Cohen, and many other talks were virtual, and very, very honored to be invited, and thanks for all the invitation and host. Thank you for coming to listen to this talk. I hope this talk can tell you something. I'm excited, and I hope that it also excites you. Okay. This is a work. This talk is based on a joint work with a lot of people, including my former student and current student, Yury Zemlyanskiy, as well William Cohen, now at Google Research and CMU, as well a bunch of our Google collaborators in various branches of Google Research. So the title of the talk is something actually probably very common nowadays. It's called extracting information from text into memory for knowledge-intensive tasks. Pretty much not too descriptive, not very descriptive title. But I'm also going to start with something you also know very well, at least for this audience. So in the last X number of years, we see large language models as knowledge source, right? I should quote and unquote knowledge. And typically what we do is we take a lot of text data and we do some kind of a large language model in training, and we end up with a neural network, gigantic neural network. And this is called a neural language model, and we think it stores all the useful information for us. Then, as a user, what we're going to do is we're going to query this neural network, and we're going to ask questions, and it's going to give the answers. This is a very sort of high level, probably not so accurate depiction of how we use neural language model today, and how it's supposed to be trained and promise good things for us. Okay. Now, what are the problems and what is good things about it? Okay. As any neural network model, neural language model can do end-to-end training, and this means that if you downstream task you care about, you can do tuning on the parameters, you get a great performance on many tasks, and the model can be recycled, used for different tasks, and it all works very well. Last few years, we also see language models being integrated with vision models and other modalities. So they combine the information from different modalities together. If you happen to have a very fancy reasoning model, try to do multi-hop reasoning, multi-hop QA, you have a specific way of doing it. You also work with other type of model for other tasks. So overall, all this integration seems to be really nice to achieve something. But there's also concerning things, point, right? Many people probably already observed, and I'll just give you one example. This way of storing knowledge in neural nets, and this is the old observation too. There's no modularity. Information is stored in many parameters in a distributed, decentralized. It's hard to edit specific atomic knowledge without retraining. So suppose after training, I realized my text corpus has some mistakes. I want to say, you know what? I want to take them out. I want to retrain. You have to retrain. And many also have observed, and then you probably have experienced. Sometimes it doesn't give you the exact answer. It gives a very good guess, and this largely possibly come from spurious statistical correlation. To a certain degree, sometimes we said neural networks can hallucinate some things for you. That's not very good, right? In many cases, we want facts. We don't want to guess the facts. Okay. So this work, which composed of several papers and many other work, try to make a point. In view of those problems of gigantic neural language model, can a dedicated memory component help? I will elaborate what is this dedicated memory component look like. But the main idea is, suppose we have such a thing. We're going to have textual data. We're going to use neural network to learn something, and we're going to put it into a data structure. And this data structure we call memory. This looks like, imagine these are like a book on your bookshelf. And every time you have a question, you could just ask the neural network, your good old-fashioned neural language model, as well combining with this bookshelf, and try to get an answer. Okay. There's a lot of questions you can ask. Obviously, what to store in this bookshelf, how to represent them, how to index them, how to use them. So hopefully this work will elucidate some of them, at least from our perspective. Okay. So with that, I'm going to talk very quickly about some of the background. Again, some basic technology and terminology that many of you are very familiar with. I'm going to give a very simple set of ideas that illustrating this memorizing facts. Then I will talk about a system called mention memory, and I will go a little bit detail on that one. I will be initially going to talk about something else related to semantic parsing, but I decided it may be too much and not necessarily consistent, coherent. And feel free to interrupt me if you want to clarify things. Okay. So BERT, all the variants of BERT. And I think this is the basic building elements of modern models. You have a sequence of tokens, and they go through something, transform layers, go through a bunch of nonlinear transformation. Out, you're going to get a sequence of embeddings, and those are the real vectors representing, in a way, representing each word's meaning with respect to the context in the sentence. This is typically how we interpret what BERT does. Okay. Now, how do we actually use BERT to acquire knowledge? We actually have something called pre-training task. In a pre-training stage, we mask a particular token and ask BERT or transformer layers of the transformation, use the rest of the token and try to predict whether we got the correct token. And you do this over a very large text corpus, and you get a very satisfactory accuracy. And then your model is trained. Those transformer layers, as well as these tokens embedding, can be transferred to any downstream task. And using those pre-trained model as an initialization point, and your downstream supervised learning signal, you retune the parameters, this and that, and you can get a good performance. In that way, we say knowledge being transferred from text corpus to the downstream task data. Okay. Now, I sort of mentioned that. Acquiring such knowledge requires you store the knowledge in lots of parameters. And on the right-hand side, you see a very poorly drew, schematic depiction of transformer. And it's just a bunch of transformations, and we have a lot of parameters. The modern ones typically has hundreds of millions minimum, for a smaller model to billions of parameters. Now you capture this knowledge by increasing the accuracy of your pre-training task. This is typically called a masked language task. And for example, let's say Paris is the capital of mask. If you predicted the France, okay, right. The hero who killed Medusa was from Rome. That is incorrect. So you didn't get this information correctly. And as I mentioned previously, every time you need to add or remove certain knowledge from your corpus, you need to retrain the big models. So that's very costly. It's very hard to maintain knowledge this way. Okay. So I'm going to talk about two simple ideas at the entry point: how to avoid this issue, how to use knowledge a little bit more explicitly instead of using neural networks parameter. And they're straightforward and simple enough. Let's think about this motivating example. So suppose I've been asked such a question. I want a film recommendation, movie recommendation, and I really don't know how do I describe it. So I just use natural language expression to describe it. I want a film like Mission Impossible or The Italian Job that have big scenes where the characters must break in or infiltrate someplace. Okay. Now there's a lot of movies probably fit into this description. And I just look at one of them. I picked one of them. This is National Treasure. It does involve the main character breaking into White House, try to steal Bible or some Library of Congress. I forgot which one is which. Okay, so this is the real sort of a scenario. And the insight from this simple motivating example to see that if I want to put everything in a vector space, thinking about embedding, I would want this movie, National Treasure, in an embedding space that is close to all the things described in my query. The query has a lot of tokens, whatever. Suppose they can also be put into embedding space. I just want that. And this actually leads to the first idea is we're going to take every entity that we know about, we care about, and treat them as a token and give them embedding. So every entity now becomes a vector. So this is the movie, Seven Samurai. You know, we have a lot of information about this from Amazon reviews, a lot of text description about it, from the metadata that, you know, categorize information about this movie. Then from movie lens, you can see a lot of user added text. By no means, any of those information is comprehensive or consistent. They can be contradicting to each other. They're probably missing some things, especially in movie text. Some of those texts are not curated well, and people just put it there. Okay. So our question is, how do we actually take all these?
I just have to ask, isn't the first review about Rashomon, not Seven Samurai?
Oh, maybe. I don't watch movies. So maybe I should have blamed my mosquito tonight, right? That's all right. Maybe I copy paste in the wrong place. All right, good catch. Maybe see, that's a contradicting one. That's not an accurate one. So how the question is stands that how do we pack all this information in a vector that's to represent the seven samurais? This is the idea behind this work. The intuition is, as I mentioned, entity embedding should cluster around embeddings, all the things about it. If we can, for every entity, we have declarative knowledge. What we're going to do is, for every piece of declarative knowledge, we're going to find the embedding, and we want the entities embedding to be centered among those embeddings. And so, just very simple schematic example: the red one corresponding the first entity, the green one corresponding the second entity, and then we have a tag embedding, we have a sentence embedding, and you know they're separated, right? Schematic. And turn this intuition into models. This is the work we did. And very simple model. This is representing a positive example of embedding that we target at. Let's say we want to embed this one. And we take all the sentences, tags, and reviews, metadata, channel them through a BERT model, to compute the upward embedding. We want this two to have a positive inner product. On the other end, we have a different vector embedding. For another entity, we want them to be far away from each other as a negative example. It's a very simple idea. And all the other two models just a variance of the same. Right? This actually works. And we are not the first sets of work on this. There are other similar works on this one. I sort of just picked some examples from our blogs. And so on the right-hand side, you see queries like that. On the left-hand side, you see top 5 results from the movie recommendations. And the brackets on the left-hand side is just something we masked out and hope that the movie recommendation system built on this way, or the model will answer with items including this. Okay, and you can see the first one is whiplash and actually gets recommended in the top 5. The second one is the drive or the robot. I didn't watch any of this. I only watched the Italian job. So nonetheless, they are all being recommended, and I think that's actually good to know. The model is learning some useful things just based on some description that is not in the training data and purely zero shot in the sense user can write anything about what they want and get the right sets of representations. Okay. So this is the first idea. To summarize, that idea is take an entity, make a vector out of it, and make it close to something else. Now I want to contrast with another. This example is about a question answering that requires you to reason over multiple entities, but a very long range dependency and relations. So many people here probably read a lot of Rings, or at least watched the movie. Okay. It's a very long book. So let's say this is a probably hallucinating example. I haven't tried it myself. Frodo could not throw something into the fire. Okay, the ring, right? I mean, we read it, we know it, we memorize it. But if you ask a bird about the answer, the argument here is that it doesn't remember in the beginning or in the end, the ring slowly gained control of Frodo. So therefore, there's a mention of the ring and the mask likely refer to them. So if you have this auxiliary information, you will be answered correctly. The question is, how did you get this auxiliary information? The simplest solution, just true false. If possible, you just put all the books into every token into the bird. That is the descendant down. Bird, as we know, has an input limited to 512 tokens. No way you can do it. And there's many books or articles, documents, more than 512 tokens. And this is just an example of a bunch of books that consider the longest books, I think, the planet. Into some of them has 1 million, 2 million tokens. Okay. And the upshot is bird's computation complexity is quadratic in the number of tokens. So therefore, this is just practically impossible. Now, what we can do. Now, this idea called read twice, and it's very simple too. Okay. Essentially, just like the following. We're going to chop up a very long piece of text into shorter segments. We're going to read each segment independently. Once we finish reading them, for each segment, we're going to extract a bunch of information, vectors. We're going to keep them around, just saying this vector represents what is this information about this segment. Then we do second time reading. This time, not only we read the segments, but also all those vectors from the first pass. Okay, it's just like as the name of the method alluded to, read twice. Okay, there's some schematic depiction of that too. Okay. On the first read, now I'll tell you a little bit more. On the first read, as I said, every segment, in this case here, I just use 2 sentences example, will be read, sort of independently. Now, the first one has Frodo, and I put a bracket there, meaning this is the entity we care about, and could not throw the mask into the fire. And the second one, the ring, slowly gain control of the Frodo. We also get an entity from the ring, but also the second sentence also refers to photo. So we also get another embedding. And this embedding called a mentions embedding, which will come back later on. But nonetheless, we're going to, for every of mention of every entity, we're going to build out a table for it. So this table will be number of mentions of all the entity we care about. Oh, sorry.
Just a very minor question. How do you use BERT to get a representation of a multi-word phrase like the rate? Do you take the average, or you take the last word? Or
Good question. Yes, I will mention that, but let me give you a quick.
It's not very.
It is actually interesting question. It bothers me, so I'll mention how to go.
Okay, thanks.
The multiple ways to do it. The simplest way is pooling, average, whatever. The little bit fancier way is take the two tokens embedding, go through linear projection layer, and that's adaptable. The third way is put a special token start and end mention, and you just concatenate the start and end as the.
And you retrain BERT to know about those special tokens.
Yeah, you retrain BERT. You have to redo the pre-training task again.
Thanks.
Yeah, but it's one time.
Does this end up mattering a lot?
Actually, we never actually tried it different ways because they get used in two different work. The one actually eventually I will talk about use the start and end token as we have. Okay, so I think we've done this one. Now, how the second rate happens? As I mentioned, once we finish reading, you get this table, right? This table is just a collection of vectors over there. And there's the first two. You're going to rewrite those sentences. However, now you have attention over this table such that you're going to pick up whatever vector, you're going to treat it as token and you just pick it up to participate in computing the embedding for photo, for the ring, okay. And this table is just written down there as because so far we have three entities we care about. Okay, so I'm not going to give out any other details, just referring some of the results here. And for this one, we tested question answering over both. So that luckily there is a benchmark data set called narrative QA. So passage is essentially either a book or movie script. It's very long. And therefore, on average, it's 62,000 words per document. And you have to ask questions about this. There's certain method can actually rate 62,000 tokens per at the input. You just do some hacks, some interesting model design, you will be able to deal with that too. And we're just using two of them. One of them is called Roberta. The other one is EDC. EDC can actually process passage up to 5,000 tokens. This is the results. The evaluate bunch of the standard retrieval metric. And we got improvement results, and good to know it works. You should read your books twice in order to answer the question correctly. The important thing is to find out memory tables actually helps. So just by going through your segments twice and be able to record all the embeddings, that will allow you to actually recall information about the passage you previously read, such that you can assimilate those entity informations and improve your performance. We already went through this one. Okay. So I want to actually use this to showcase, memory is a data structure, and there's many ways of designing a memory. And this one just, by the way, I want to check, what is my time?
Till 1 or 5
Okay, thank you. So there's many ways of designing memory. So there's not a specific memory doctrine. So the ways of thinking about memory is the many axes design it. First, how did you represent them? Do you want a raw piece of text as part of your memory table? That's possible. Now, the problem is, the good thing about it, there's no information loss. The problem is it's going to be very expensive because in order to do it, you have to use another reader to read it, become a vector encoding. Okay. In the Dawson work, entity, every piece of information we care about entity is compactly represented as one vector. So it's the most compact, but it's efficient, but then it has an aliasing problem because then sometimes entity has overlapping dimensions, they adopt product, not at all. Exactly problem. The previous one is called entity mentions, which I mean the multi-phrase, those kind of things. They are highly contextualized. For every mention of a particular entity, I come up with an embedding, I put into the memory table. Last time you see photo appeared twice instead of in the dozen one will appear only once. You can also think about how to store them. Okay. You can store them offline table, like I showed. They're very cheap. During the runtime, you just need to retrieve, and that can be accelerated very fast. And problem is, now if you have new questions, want to ask the model, the new question cannot be used to change the embedding of what's in the memory. It's frozen, it's fixed. However, on the other way, if you do it online, you retrieve the text, you can attach your query, your question to it, and it can change it adaptively to the embedding, and that's give you much big flexibility and in exchange for very high computational cost. Jason, do you have a question? Okay, all right. You can also think about an index structure, how it can be done. In the index structure, you can use actual retrieval model to do it, and some work does it. Or like we're going to talk next, we're going to use attention-based retrieval mechanism to actually retrieve the information we need. On the right-hand side is a partial list of a bunch of work have this kind of memory augmented NLP models, and you know our work is just complement many of them. Okay. So now let me jump into this work. I really want to highlight. This work took us some time, and it's both you know, from modeling perspective very challenging, but also from engineering perspective, it's challenging too. So I'd like to share with you. And again, this is the work led by my student Michiel and Yury, while being hosted at Google. Okay. Again, this motivation, let me rephrase again. We want to treat the text as a virtual knowledge base. This is the Benoit discovered this on an article a couple of years ago, and traditionally we have information in a regular normalized database look like this. We have a property name, we have property values. On the right-hand side, what we're going to do is we're just going to actually directly use the text instead of try to extract them and try to normalize them into the database. Okay. So the high-level goal here is trying to achieve open domain question answering. So now instead of looking at a lot of rings, what we're going to do is take Wikipedia has a collection of information about a word, and we want to compress into a memory table. And then some neural network reasoning model or question answering model will answer the question for us. Okay. Now this time the question is answered correctly. Okay, so this is the model architecture. It's a bit of a busy, so that allow me to explain a little bit. First, we're dealing with the Wikipedia, so we extracted 150 million entity mentions. And again, each mention is an entity appeared in a sentence, and about 150 million mentions. And then we use something called a pre-trained mention encoder. I'll get to the details. It's a special reader, and I require a special training. And it regenerates a memory table, and this memory has a key. For each entry has a key and that corresponding to each of the mention. And to use this memory, we're going to revise the standard transformer model. We're going to have something called a transformer block. In here, we're going to have, we call it the tone block. And in there, the memory attention layer will be augmented with all the entries in the mention memory. We're not going to run attention over 150 million. I'll explain how we do that. But then the memory attention will then generate something, will fit into the transformer block. Okay. There's a specially designed initial transformer block that looks like just regular transformer. In the tumor block, as I mentioned, we're going to for each of the input passage, we're going to represent and store the mention encoding, retrieve top K relevant mentions through attention. And this top K is achieved using dot product to do nearest neighbor, fast nearest neighbor search. And then we can fuse with the current input mention representation and then fit into the transformer block. This one can be stacked. The block can be stacked several times. Previously, I mentioned that the memory table like this has one disadvantage, that you really cannot change its representation once it's frozen, no matter what kind of input you can have. However, you can sort of elevate this problem by using two Tomor block, because after first Tomor block, the representation of coming out of input dimension already been changed, hopefully carries both query information and your memory table, then you're going to transform it again. So this is the workaround, and hopefully they achieve some kind of multi-hop reasoning and reconditioning by the query. Yes.
So I have a bunch of questions, but maybe I should wait because you're probably going to answer it.
Yeah. Go ahead.
Yeah. So one question is, you were concerned before that the book was going to be long, and so attention would be linear over the past context per token. You still have that scale problem here, right? Because the memory could be very large. So are you doing some kind of approximate attention using locality sensitive hashing or something?
Yes. Using we only retrieve top K, and the top K is done using approximate nearest neighbor search. And the nearest neighbor search actually used the memory key and the input, the output of the one of the transformers keys to match it up, do inner product very fast.
Yeah, that's perfect. And attention over those top K things still sums to one, or if none of them are good matches, do you have it sum to less than one?
The top K, we only retrieve top K mentions, and those mentions been attached to the input tokens.
Yep.
Attention is all over there. It's like almost like a self-attention layer at that point.
Oh, I'm sorry. Are you saying you attend back to the Wikipedia text?
No, we don't.
Yeah.
So at this stage, once we build a memory table, the Wikipedia text is already thrown away. It's gone. Yeah. Good. Okay. All right. So as I alluded to, it turns out this is, to a certain degree, it looks like a beefed out version of the Retrieval, but actually it's not. There are several challenges there. First, how to actually read the Wikipedia text and frozen them into in a table. So we need something called mention encoder. This is a specially designed training procedure for it. In high level, it's pre-trained a massive language model and some auxiliary tasks. If most importantly, froze the memory table, and once it's trained being used, it's not going to do end-to-end training. You cannot tune the table anymore. In the phase 2, the tone block, that's the one also has its own pre-training stage. So I'm going to get to some of the, especially phase 1. The mention encoder turns out to be the biggest modeling challenge. It's actually a catch-22 problem in hindsight. We want to store the text in the memory such that it will produce useful information for the tone to use, for the neural network reasoning model to use. But then the reasoning model hasn't been trained yet. So therefore, how do we know whatever encoding we have for the mention would be useful? It turns out that's the chicken and egg problem. We walked around this problem. I mean, ideally, you would want to train it using some EM style procedure, but it's going to be very costly. So we opt for a very smaller version of this model training procedure. What do we do is we actually sort of using a minimum tone called a badge tone. Every time when we do master language tasks on the mention encoder, we look at this small set of memory in the badge, and we try to say, okay, if I put this badge into the tone model, would it actually recover the right set of entity? Would be able to retrieve them? And that's the minimal sanity check question, right? If I put something in there, it's already there, it should have been extracted. Okay, so this is the auxiliary task, is to recover the masked entity code reference. And this is our specially designed pre-training trick. Details again in the paper. So for the evaluation, what we did is open domain Boolean QA claim verification task, the two of them. One is a favor, the other one is hope. The first one actually can resolve the claim verification using one single Wikipedia page. So actually you don't need to, you could solve it using more than one. However, on the other hand, requires multiple Wikipedia pages. It's in this particular example, the claim is Patrick Carpenter currently drive the Ford Fusion, introduced model year 2006 in NASCAR. And actually, this requires two evidence supporting passage to make this claim true. And they appear at the two different Wikipedia pages. Okay. So this is the more from a multi-hop reasoning version. As Jason already mentioned, once we train the model, there's no more Wikipedia text. We go back to check this. Everything is in the memory, all the knowledge is in memory. And this is the result we get with some state-of-the-art models. Tome 1, Tome 2, just the different variants of original code. Tome 2 has two tome layers for mimicking multi-hop reasoning. And in order to keep the computation the same as Tome 1, so it has a smaller number of tome logs. Okay. So we got the state of art on these two tasks. We can also do open domain QA tasks. These are all the questions with entity as an answer. And it's including three data sets: trivial QA, complex web answers, entity questions. So trivial QA is just like a single statement QA questions, I believe. Complex web questions requires conjunction and composition, understanding of the query. Entity question is actually asking a lot of things about rare entities. All those entities actually can be found on Wikipedia. Again, this is the model that's running without access to the Wikipedia text. Okay. We can look at how memory size matters. Previously, I mentioned we used 150 million mentioned memories, so it's pretty big. What we can do is actually to mimic the sort of fine-tuning training size. During the fine-tuning stage, we will only use 1/5 of it, like 38 million mentions, and nonetheless, we keep increasing the number of entries in the table, mentioned the memory table. As you see, as the memory goes up and the performance gets better. So that means that the more you memorize from Wikipedia, the better your performance will be. Some interesting tome retrieval results. This is the I think this is the whatever, forgot, maybe the cover number 1. The first sample. This says Greater Swiss Mountain Dog and Harry are both dog breeds. This label is true label. And this dash 1 actually refers to the first layer retrieval results. And for both two entities here, we retrieve the corresponding Wikipedia passage and in this case correctly, and they're both referring to the dog breeds. Okay. This is a fun example talking about how would you do multi-hop reasoning with this memory structure architecture. Again, the claim says the sound recorded by Pretraining that was produced by whatever and was followed by life goes on was this label true. So the first retrieval of life goes on is actually incorrect one. It has nothing to do with not sound. Okay, and the Hungary, the first retrieval results is actually irrelevant. It's accurate. It is related, but it is about the producer, but nothing to do with the questions. Now, remember I said we're going to do the second retrieval after transforming, taking into consideration both the mentioned memory and the query. And we're going to have the second retrieval. This time, the light goes on retrieved correctly as position of the this song in the album, and Hungary is also covers all the information you need to resolve the claim. So the sort of multi-hop reasonings. Yes.
Is the first retrieval for Hungary actually irrelevant? I mean, it does say that Michiel de Jong did produce a song called Hungary recorded by Fergie. It doesn't say it was followed by that design.
Yeah, I think it's irrelevant in the sense, I guess, it didn't have life goes on, or alone doesn't actually really, I guess coupled with life goes on really doesn't actually can answer your question, right? I mean, maybe you will consider it as relevant.
Might be relevant that it,
Yeah.
you know, narrows the set.
Yeah, I guess so. I guess you're right. I guess so. Maybe I should give more credits to this retrieval, this particular one for Hungary. Okay. Thank you. A lot of detail I didn't say. First, retrieval through attention. I think Jason exchanged a little bit there. Essentially, you use a fast nearest neighbor search to attend to 150 million. Yes, we are not going to attend to all of them. Subset of them. The nitty-gritty details, pre-training tasks and objective will be in the paper, so we're not going through them yet. Important property information encoder. I think I was talking to one of the Ben students, right? Oh yeah. So in fact, in our paper, we take the mention encoder to do fine-grained entity typing, actually get the best state-of-the-art result too. So the mention encoder alone, that training criteria and the structure alone can be used for other tasks in addition to doing question answering. I didn't talk about another interesting property that is during the inference time, you can dynamically change the memory, in the mentioned memory, and you can add, delete this and that, and it will be easy to do. So far, actually, the memory table can reside on single compute node, so it's actually quite compact. Even it has 150 million mentions. So let me conclude this by pointing out a few nice things about this work. The architecture essentially used the contextualized representation of the entity as external memory. It made it more precise because you actually get to know all the context. It does retrieve efficiently and inference efficiently. The fast neighbor search compared to transformer is just nothing. It's a very small fraction of it. So it actually doesn't have too much computation latency overhead. It doesn't increase their memory in the GPU memory. The drawback, as I said a few times, it doesn't adapt to a new representation equal chain query. It's stay frozen. Training is indeed complicated. You need 2 phase. In fact, the 3 pre-training schedule to do in order to integrate well because it's a chain problem. There are many really nice work and related to this. If you contrast our work to those works, it just represents different design choices. You know, models like retrieve and read, those are interpreted more broadly is also type of memory models, and our work is very different from that. There are a lot of limitations about memory based NLP model, augmented model, not just to us, but to many other work too. So far, we can only deal with declarative knowledge, right? We can store the facts reasonably well now, and we can even use it to multi-hop reasoning to various degrees of success. We still rely on neural-based model for conceptual or procedural knowledge. We actually don't know how to put those declarative knowledge together as a coherent piece easily. We all hope the neural network, the transformer, will do the magic once we get the basic facts right. And that is a big deficiency at this moment. I'd like to thank again my co-authors and many people besides these 3 collaborators who actually heavily influenced this work, did all the heavy lifting of engineering. Thanks. Any questions? Yes.
So I'm wondering about scalability, or I guess reducing the footprint on the value embedding side.
Reducing
The footprint on the value embedding side. So I'm wondering, and I apologize if you mentioned it baseline. How much of a performance up you would get if you had done the same thing on the query computation side? So you're doing mention identification at inverse time. But you're trained because it's a separate training procedure anyways for training the attention weight, the mechanism. Why not just optimize it for retrieving the bird embedding the full passage like you mentioned, as opposed to having and different embeddings for different source type?
Yeah, so that's a really good question. So I mean, just to be honest, I wasn't when I was first looking at this work and I had this idea, I wasn't quite getting either. It turns out there's a lot of details. Retrieve a text, then read again, has two issues, at least two issues. First, in such models, encoder consume a lot of computation. That's why the decoder only model tends to be better in the sense decoder is. That's the first thing. It's actually computation very heavy. Secondly, because you're reading raw text now, you append it to the input text. You run the risk if you retrieve multiple passages, you very quickly.
I'm not saying retrieve passage. I'm saying take the bird embedding out of the map. So instead of doing all the work to compute the embeddings of the entities, dimensions in the corpus, just compute the embedding of the full passage and not have to do that multiple times.
Just compute the embedding of the full passage.
Right, and so if there are any mentions in the passage, you just retrieve the same embedding regardless of which of those mentions.
Okay. So that is alternative. So in that case, I don't know whether we did the experiments. If you think about the first word, simple idea described, if you throw away all the tags, all the other metadata, and we have a review tags, that would be more of as you were describing. I think it's good baseline. I don't recall the number or even we did extract, but upfront you're losing resolution passage with multiple entities. That's one drawback.
Right.
Yeah.
I have a question which may be based on misunderstanding something you said.
Yeah.
So when you have your mention table, right, and you do this nearest neighbor type retrieval for the top few.
Yeah.
One of the things that I'm thinking about is that if let's say there's a set of entities which have a small set which has many mentions, and a few other entities which are related to your question, but which have very few mentions. And you can retrieve the top K. You might be retrieving many mentions of the same entity.
Yeah.
So is there any way to create diversity in the retrieved memory block?
Yeah, I don't think we did anything specific. The counter argument is actually, since we really care about looking at the dimensions in the input token, in the input text,
Right.
you would actually want really care about the entity in the input. You really care about whether you retrieve the things really about those entities and their related mentions. Therefore, it has a risk without looking at diversity. That is, what if I need a multi-hop? Like if in my input I have entity A, but I really not answer the question, I need a B, and B is related to A, C is related to B. Now, when I retrieve things, I retrieve a lot of A, but less B. That is problematic. But if you don't have a lot of such problems, then just retrieving A is not such a big deal.
You drew many queries, right?
What?
You drew many queries, right? So if I understand right, you're encoding the question.
Yeah.
And parts of the question that talk about entity A
Yeah.
will tend to get mentions of entity A, and parts that talk about entity B. Entity B will have a query that tends to get back mentions of entity B.
Yeah.
So,
But I think Jeff's question is, if this question only have A, right? Mention the entity A, and when I retrieve mentions from mention table, is only about A. So I wouldn't be able to solve problems if actually solving the question I need an entity B. and B is not actually in the mention. So
I'm in fact worried about the other one, that the
Uh-huh.
question mentioned B,
Mhm.
but B and A are similar enough,
oh,
and A dominates your counts. So if you do the A nearest, like,
Mhm.
maybe just by going, in other words, I'm thinking about how when you do information retrieval, you think about incremental or like, differential information, right? What's the next document you use? So I'm thinking about it from the retrieval point of view, it's one diversity in between.
yes, great question. So this is actually started in the second bullet point.
Okay.
So the design of that auxiliary task
Yeah.
is not only use the objective, but also checking to make sure indeed you can get the right certainty. Yeah, so you wouldn't be flooded with the exactly similar one. So the accuracy there is 55 for mention included. So it's a relatively high accuracy for pre-training tasks. So certainly you can do better, but I think that's good enough at the time.
Yeah, what is it?
Always, but other people have questions.